Hello, and welcome to the first class in the Fundamental Concepts in Chemical Engineering, our overview course at Arizona State University on teaching chemical engineering concepts to non-traditional chemical engineering students interested in pursuing chemical engineering graduate work. My name is Christopher Muick, and I'm an associate professor here at Arizona State. I'm one of the instructors that are going to be guiding you through this semester and class. Today, we'll do a welcome and an overview of what chemical engineering is. Then we'll go through some course information. We'll talk about our syllabus. We'll talk about the course and the class structure, and then secrets of success. So first, I want to go through and discuss what do chemical engineers actually do? Well, chemical engineers design, select, organize individual steps to do a transformation of raw materials into useful products. What does that mean? That means that we take some sort of liquid, gas, or solid and transform it into some sort of other chemical material. Or, put another way, we take some sort of substrate, represented here by S. We do a series of transformations, some of which take energy, and we turn that into a higher value product. Hopefully, in a process that minimizes CO2 production, is safe, and minimizes waste. Some example substrates could include biomass, oil, raw oil, different mineral ores, and things like the air. Energy inputs can include things like heat, light, mixing, pumping, and products include pretty much everything that you use every day. These include things like pharmaceuticals, vaccines, batteries, semiconductors, energy, processes for environmental remediation, your toothpaste, cosmetics, cleaning products, paper, and even food. So, how do we think about chemical engineering and think about that as opposed to sort of chemistry or physics or the other basic sciences? Well, I like to think about it through this analogy. How does one bake a dozen cookies? Well, you crack some eggs, you measure butter, sugar, flour, baking soda, etc. You mix them together, you form it into your desired shape, you put it in the oven, bake, and then let them cool before you enjoy. But this is only a dozen cookies, right? In the real world, if you want to do something industrially, you need to make thousands of cookies an hour. You still need to do all of these same steps, such as cracking eggs, measuring out butter, sugar, baking flour, etc., mixing them, forming them into a shape, moving them into an oven, baking them and letting them cool. But it all needs to be done in a process that's seamless, integrated, and profitable, right? Which means minimizing waste input, right? So you don't waste sugar, flour, etc., and you don't waste excess energy, right? You want to make sure that the ovens are operating at peak efficiency and all that energy that's spent is going into the baking of the cookies themselves, right? So this analogy I sort of like to say is analogous to, chemists, right? A chemist might come up and say, hey, this is, or a biologist might say, hey, this is a brand new drug that we want to deliver, and it's going to, cure some sort of disease, right? But it took that chemist or a biologist weeks or months to come up with a formulation and carefully make that material. This is never going to be industrially uh, uh, extendable if each person, if a person has to individually make these. We need to come up with a process that can take those raw materials that went into the drug and produce that on a massive scale to make hundreds, thousands of tons a week or even a day. Right? So, like I had mentioned earlier, chemical engineers solve some of the most important problems. Here are the 14 grand challenges outlined by the National Academy of Engineering. And chemical engineers play a large role in all of these, from making solar energy economical by improving the production of solar cells, managing the nitrogen. How can we cycle? How can we extract nitrogen from the air to make fertilizers? All the way through health informatics, um, uh, engineering medicine, and clean water. How do we do that? Well, we have we do that through combining uh, key concepts in chemistry and physics, along with tools such as calculus and numerical methods and different laboratory skills, in with sort of engineering principles of transfer. Transfer. So this can be fluid mechanics. So how do fluids, gases, and liquids move? Um, or how does heat move, right? So if I have something hot touching something cold, how fast does the heat move from the hot thing to the cold thing? How does mass transfer? All right, so think about this as if I have a drop of dye, put a food coloring dropped into water, how quickly does that food coloring move through the solution? Right, and this is going to dictate the speed of how material and energy can move through space and time. We also have a detailed understanding of thermodynamics, right? So what are the underlying thermodynamics that describe whether a transformation in a material, whether that be a phase change or a change in the chemical structure, actually happens? All of these lead into some of these more advanced classes, such as reaction engineering or reactor design, where we design the vessels for processes for taking two different substances, combining them together, and undergoing a chemical transformation to a desired product. Of course, when we mix things together, we also need to separate them apart, right? So if I have a mixture of things, how do I separate them? And to do that, um, we use separations technologies to understand how to do that efficiently. Throughout this, these all feed in and are run by controls systems that lead into design. In this class, we're going to focus on the core subjects that are necessary for engineering at the graduate level, chemical engineering at the graduate level. So this involves a transport phenomena, so fluid mechanics, heat and mass transfer, thermodynamics, advanced thermodynamics, so here, and reaction engineering, shown here. These other classes, we'll touch briefly on design, but these other classes, separations and controls, are advanced topics that if you are interested in, we highly recommend that you go back and take those undergrad classes. Okay, so what is the purpose of this class? The purpose of this class is to provide the fundamental chemical engineering principles necessary for graduate level engineering coursework, right? So we want to make sure that you have the baseline skills necessary to succeed in the master's or PhD level. This course is not designed to make you a full in-depth expert in these individual subjects that you would receive in a full semester long class dedicated to each topic. So really, you should view this class as your opportunity that provides you an ability to be ready for graduate work, right? So all the courses in chemical engineering are going to assume that you know the content that's in the content that's condensed into this class from all of the undergraduate classes. You will get out of this class what you put into it, right? So we're going to provide the overviews, the fundamental head into your mind and your way of thinking so that you're ready for graduate level chemical engineering coursework. So specifically, like I mentioned, by the end of the class, you should be able to conduct mass and energy balances. You should understand macroscopic and microscopic fluid flow, understand heat and mass transfer and their related governing equations. You should understand the basics of applied thermodynamics and how to conduct thermodynamic analyses of chemical systems. And you should understand chemical reaction kinetics and how to design chemical reactors. To cover these topics, we've broken them up into sort of two sort of general concepts. So we're calling them our tool subjects. So this is math and science review, and mass and energy balances, as well as our tested subjects, fluid mechanics, heat and mass transfer, applied thermodynamics, and reactor design. These will be our 4 exams, and these will be what's tested. In order to complete these, you will have to have the level of calculus and chemistry and physics that we will cover in our review, as well as the concepts in mass and energy balances. On our Canvas web page is where we'll provide a lot more information, and a preliminary schedule of how and when we're going to cover these topics is provided there. I will note that that schedule is slightly subject to change, but it should provide you a good idea of when the exams are, as well as when different topics are being covered. Okay, so this class is a hybrid course. The lecture materials will be provided online via YouTube videos. These are linked in on the Canvas webpage, and you can go and find them there. I just want to note that unfortunately, we, the chemical engineering faculty, do not control YouTube ads, so we're not controlling what you may or may not see, nor can we turn them on or off. And of course, we don't get royalties. Um, After each lecture, that a lecture will be assigned every day, Monday through Thursday. Friday is a day for you to reflect on what you've learned, go over things, do practice problems. So for each of these classes, there will be a timed comprehension check that will require you to, show that you've watched the video and have a basic understanding of what's happening there. We'll then have 4 exams covering each of the subject, and then we'll also have practice problems with solutions given. Um, just due to the time constraints of condensing so much information, we unfortunately just don't have enough time to go over reams of different types of practice problems. Therefore, we're providing a set of practice problems with the solutions separately on Canvas to give you the chance to do practice runs. So the content that we provide here should provide you the information necessary to do those practice problems. Okay, so in terms of grading, we have the final grades will be assigned based on 80% of the exams, 15% on the comprehension checks, and 5% on professionalism and participation. The exams, like I said, will be open book. There will be 4 of them. There will be open book, open note, each one covering one of those 4 key concepts: fluid mechanics, heat and mass transfer, thermodynamics, and reaction engineering. And they will be assigned online via Canvas. Students who are participating in the Catalyzed Transition to ChemE program, and therefore have undergrad deficiencies they must make up, have to achieve a 75% or better on each of those different sections to have them counted, and remove that deficiency. Okay, so comprehension checks. These are going to be a few questions that should test your understanding of the various topics. So light math may be required. They'll be on Canvas. It's a one-time only timed test without repeats, except a practice quiz, which you can take over and over just to get used to the Canvas uh, system. To find them, if you look on the left-hand side of your screen, you should see a button that says quizzes. By clicking the quizzes, you can link to the quiz itself. When you first open that, you can click the link to the YouTube video. It'll take you right to where you need to be. In addition, we have points associated with participation and professionalism. So in terms of participation, these will come with surveys and end-of-class evaluations to provide us feedback on how to make sure that this class is running well and we're continually improving, as well as participation in discussion boards. Because we're mostly in this hybrid modality, not everybody is going to be doing these and having questions at the same time. Therefore, we've provided a discussion board where you can post questions, answer other students' questions, and deepen your understanding of chemical engineering fundamentals. Okay, so anything that's not grade related, right? So, anything that's, professor, I didn't understand this concept in fluid mechanics, for example, please put that first into the discussion boards. And then if you feel that you have a good understanding, please feel free to answer other students' questions. I promise you that if you're having a question on a topic, some other student is also having a question on there. So when you go to the discussion boards, check within the different topics whether that question has already been asked, and then go from there. We will be regularly checking that discussion board and adding feedback as if classmates don't do that. In terms of professionalism, we expect that all emails are both to the faculty and other students are written in a professional manner, and discussion boards are handled in a professional manner as expected of um, uh, a professional engineer. Just to show you where the discussion boards are on Canvas, you should see a link on the left-hand side that says discussions. There's a link, a set of discussion topics. For example, there's general class questions or science and math review. When you click on that, you should be able to post something to that board. Okay, so moving a little bit back out of some general course topics, I just wanted to take a second and acknowledge that engineering is difficult, and transitioning to engineering and chemical engineering can be hard for a lot of students. Why is this? It's because students have traditionally, in a lot of topics, sort of been shown, here's a few examples where they see a problem statement or equation. There's well-defined, predetermined steps to solving those, or the equations are pretty much the same. We're just altering numbers, and then you can show up at a solution. This is not what engineering is. Engineering starts with a general word problem, or a problem that must be solved in the real world. It's then the responsibility of students to assess the chemistry and physics that are happening in the system and derive their own equations or modify existing equations. This often requires additional information and or estimations or assumptions, right? So only after you've solved the critical thinking problems over here do you end up with a set of equations, which can then be set and then the mathematical processes commence. All right, so how do we think about this? We're mostly about problem solving, which leads us to physics or chemistry. That physics and chemistry will tell us what type of math and usually what differential or integral calculus problem we need to solve, and then we can go and solve that. And sometimes we have to do this loop multiple times in order to tackle individual problems or parts of a problem. Okay, so how do you succeed? First of all, make sure that you're doing the practice problems. We've assigned these practice problems because we think that these will give you the broad overview of these topic areas so that you can excel on the exams and in your life as an engineer. Please learn as you go. This class is both fast-paced and it builds upon itself. So you're going to need the chemistry and calculus to understand mass and energy balances. The mass and energy balances combined with calculus and physics leads to how we can think about fluid mechanics. Those concepts move are going to show up repeatedly. So don't think that by just learning for the exam and then forgetting, that's a good way to go about it. You really are going to need all of these topics as you move through the course. We highly recommend that you don't try to memorize are conceptually similar to what will be on the exams, but are not going to be the same. So don't think about it like the numbers, the problem statements are going to be the same and just the numbers are going to change. What we're looking to see is, do you think like an engineer? Can you problem solve? If you're having problems, get help early. Um, whether that's through study groups, um, tutoring, the discussion boards, or office hours. So office hours, of course, will be on demand. So email me if you'd like to schedule some. Email me or the appropriate uh, uh, professor who's leading the section of the class that you're in. Okay, so ask and answer questions on the discussion board. You students are your own best sounding board. By helping each other, you're going to cement these understandings and processes in your own mind. We also highly recommend that you find some study buddies. There's a section on the discussion board for finding study buddies. Go ahead, do that. Lastly, it's very easy in YouTube online-based lectures to sort of zone out. To avoid that process, we highly, highly, highly recommend that you take notes as you go. We are purposefully not posting these notes and lecture slides because we believe that the process of taking notes will help you cement the concepts in your head and force you to actually pay attention as you go. We've found in the past that by posting lecture notes, students tend to um, pay less attention to the online content. All right, so by this point, you should now have a pretty firm understanding of the general course, what will be covered, how it will be covered, and how you can succeed. As a starting set, there is a quiz that's going to go along with this intro, so please log on to Canvas and complete that quiz. Additionally, for tomorrow, we'd like you to also complete the sort of first content chapter, which will be a review of vector calculus. All right, I'll see you next time. Bye-bye.